All right, well, welcome to another beautiful calculus day. The plan today, after we go over any homework questions you guys have, is to start talking about applications of calculus in physics. I know that most of you are probably going down that route into physics, engineering, chemistry, the sciences. So a lot of this will be important to you later. But historically, it's also the reason calculus even happened, right? The only reason calculus happened was because scientists were trying to do physics and they didn't have the tools yet. The math tools weren't there. Like when we were talking about finding velocity, like day one, right? And how velocity question ended up being the tangent line question. Well, there are all kinds of applications of physics where calculus is involved. And so we're going to start looking at a bunch of them today. We'll continue that on Wednesday. And you're going to get a little bit physics out, probably. I apologize in advance for those of you who are not into physics or going that direction. But I'm going to guess most of you are probably taking physics right now. At least I hope you are. The Physics 107. So this should probably make sense with a lot of what you've been doing in that class as well. Oh, thanks, Rigney. So 7 of you guys are. That's a fairly good group. All right. But before I start just going, homework questions. Anything you guys would like to talk about? I know that some are due tonight. All right. So Chase and Alexi at exactly the same time put in 2.4, 9, and 10. They sound like popular questions. All right. Any others? Okay, well, let's go look at 2.4 numbers 9 and 10. And if anything else comes up, of course, please let me know. Huh, thanks. I muted myself so I wouldn't cough and then forgot to unmute myself. Thanks, Alexi. So as I was saying, as you guys all heard, excuse me, we're just looking for taking this section of the curve and we're going to rotate it about the x-axis. So they actually gave us a picture of that solid, what it's going to look like, or what that surface is going to look like. But this is the typical what we're going to do, any kind of revolution surface. So what's the general formula? What do we integrate in general for surface area? Do you remember what I gave you as sort of the quick, easy thing to remember? It was forever ago. It was like last week, some point. So what we want to do is we want to integrate 2 pi RL. Okay, so 2 pi RL is the general structure anytime you're finding surface area. So that means we get to figure out the radius of the circles and then the arc length as well. All right, so I'm going to go ahead and go to a whiteboard here. All right, so we're looking at y equals 6 square root of x, and we're going from 1.4 to 4.3. At least I think that's what my numbers were. So for surface area, in general, you want to integrate 2 pi RL. All right, so let's start setting this thing up. In terms of the bounds, we're going to go from 1.4 to 4.3 because we're rotating this thing about the x-axis, right? So let's just say that that was our curve. We're rotating it about the x-axis, so we're going to see this guy, right? So that's the same general picture that they gave us. So our x's are going to go from 1.4 to 4.3. So you think about any one of those slices, we need to calculate its radius. So for some generic slice here in the middle, its radius is going to be this right here. So that's going to be the function value. So we're going to get here 2 pi. The radius is going to be 6 square roots of x. It was the function. So for this specific picture, for the specific way we're rotating, that r is just f of x. All right. Now, that's not always the case, but it's the case when we're rotating it about the x-axis. If we are going about the y-axis, our radius would have to be the x value. So we'd need a function of y. If we were rotating about some other axis, like let's say we were down here at x equals -2 or something like that, we would have to do our function value plus 2. So we have to adjust it, but that's why I like to think of it just as 2 pi RL, and then I can use the picture to figure out what my R is. Okay, so that was that piece, but now we need the length. Okay, well, that's going to be our arc length, and our arc length formula, remember, hopefully, is that square root of 1 plus f prime of x squared. So that was, again, the in general. That's how we calculate the arc length. You can also substitute this in instead of f prime of x. It could be f prime of y. If you've got this as a function of y, it doesn't really matter. But that came from distance formula. So we need to go ahead and put that in here as well. So our f was 6 square roots of x. So f prime is going to be 6 times 1/2 x to the minus 1/2, or 3 over root x. All right, so I'm going to get 3 over root x squared dx. Okay, so before we try to actually do this integral, any questions on how I got it built? We all okay with that? All right, well, let's see if we can simplify this thing. So we've got 2 pi. I'm just going to pull the, actually, let's pull out 12 pi. The 6 times 2 pi, it's all constant, so I'm just going to pull all that out. And we got 1.4 to 4.3. Square root of x times the square root of 1 plus 9 over x. And then I'm going to go ahead and distribute this root x distribute the x into this, so I have just a single square root. I think it's probably going to be a little bit easier. So let's run this up here. So we've got 12 pi times integral But now we're going to have the square root of x plus 9. All right, so there's our thing that we need to integrate. This one's probably easiest done if we do a u substitution. I mean, check this out. If you let u equal x plus 9, then u is equal to dx. So this becomes an integral of square root of u du, which is nice and easy to do. I'm going to go ahead and change my bounds while I'm at it. If x is 1.4, u is 10.4. If x is 4.3, then u is 13.3. So we're just about there. U to the 1/2, that's the square root. So u to the 1/2 becomes 2/3 u to the 3/2. And then this is purely a calculator question. Plug the numbers in and you can get your value. So at this point, use the calculator and you get whatever you get. I don't really care what the number is. Obviously the computer is going to care what the number is, but for me, at this point, I think we're good. So this is always the structure. It's always the structure of what you do. You integrate 2 pi RL. Really, the part that you're going to have to work on is the R, because 2 pi is just constant. That doesn't change. And the arc length, it's always found the same way. It's always the square root of 1 plus f prime squared. So that part, you don't really have to think about that. You do have to think about the radius, but then once you get the radius set, let's put it into the formula and go to town.
So,
all right.
Bruce, I think the problem with this question is what they ask for f of x. Like, because I got the final integral, it's the f of x part, like their first question, part A.
Okay, let me go back to that question. I guess I wasn't paying close enough attention because I just saw it said find the surface area. So I'm like, well, there you go. Okay, so the surface area, our answer now, of course, that goes down into this box. But then it says, what are we integrating? Well, what we're integrating would be all the stuff that was in. So it would be the 2 pi times the r, which was, maybe let me combine them. So 12 pi, so 2 pi times the 6 square roots of x. And then I'm going to go ahead and put them together. What was it? 9, I think was my guy. So that's what we ended up having to integrate to find the surface area. So potentially, because like, Alexis, you're saying that you got the actual surface area right, but you had something funky with that. Some things that I could see that people forgot, the 2 pi or any of the constants, right? Because we pull those constants out when we integrate. And so it's really easy to kind of forget about those. Also, and this is a potential programming issue, but it shouldn't be a problem. If you wrote it as square root of x times the square root of 1 plus, what was it, 3 over square root of x quantity squared. It should still like that, but if you put it in that way, be really, really careful with like your parentheses and everything, where the square is. on your derivative and all that. So there's a lot of potential for typing things in incorrectly, and that might have been the case. If you'd like, Alexis, I can go and look at yours later, or sorry, Alexi, not Alexis. I'll go and I'll look at yours later and see what happened, and see if maybe that was the issue. But yeah, basically they just want you to put in what the function is that you're integrating and then the answer. So this should give me points. Should. Anyway, so I don't know if that answered your question or addressed your issue or not, but yeah, no, maybe. We can chat about it later if you'd like. Well, let's just see if I at least get partial credit. Hey, all right, good. I got partial credit. That's what I get for being too lazy to actually calculate a number. All right, so let's look at number 10, see what that one looks like. So here's our curve, e to the 2x plus e to the minus 2x over 4. We're going from 0.1 to 1.2, rotating it about the x-axis. Okay, so this one says just first, find and simplify the square root of 1 plus y prime squared. So that's the length part of our integral, and then find the surface area. So we're going to go ahead and just get to the, here's what we get when we do the surface area. And along the way, we'll do the simplify the square root of 1 plus y prime squared. Okay, so let's go to whiteboard. Let me clear all this garbage. All right, so for this one, we've got that horrible looking equation for our curve. This is actually a very famous curve. It's called a catenary. And a catenary is the shape that you see if you look at like a power line that's strung between two power poles. You know how it kind of like dips down in the middle? That actually forms this shape. It's called the catenary. It's also, it also gets a name. The function for this is named hyperbolic cosine. Yeah, hyperbolic cosine. Cosh is its nickname, but that's beside the point. But here's our y. So they said let's start by looking at the square root of 1 plus y prime squared. So let's do the arc length piece. So we'll take our derivative, y prime. Okay, the 1/4 is a constant multiple. So if we differentiate e to the 2x, you get 2e to the 2x from the chain rule. E to the minus 2x gives us a minus 2e to the minus 2x for the same reason from the chain rule. So there's y prime. We cool with that one? So now let's get y prime squared. All right, well, that's going to be 1/16 times 2e to the 2x minus 2e to the minus 2x, that whole quantity squared. So we have to FOIL this out. We got to FOIL because this is a binomial being squared. So you're going to get 4e to the 4x. That's from squaring this. You square the 2 to get 4. You double the exponent. That's the rules of exponents. You multiply them together. So 2 times 2x is 4x. Okay, the outer, if I multiply these two together, I get minus 4e to the 0, right? 2x plus minus 2x is 0. The inner is another one of those. And then the last is squaring the last term. So that's from the FOIL. If you're looking at that going, whoa, I missed it, write it out. Write out the two binomials, do your FOIL. This is what it's going to look like. So this is 1/16 times 4e to the 4x minus 8, because e to the 0 is 1. So we get minus 4, plus 4e to the minus 4x. All right, so there's our y prime squared. Okay, let's just do one more thing. Let's divide all these by 4. So we get 1/4 times e to the 4x minus 2 plus e to the minus 4x. All right, so now we need to go to the 1 plus y prime squared. So we're going to add 1 to this. Well, so that's 1/4 times e to the 4x minus 1/2 plus 1/4 e to the minus 4x plus 1. So I just distributed the 1/4. So now when I add 1, the 1 and the minus 1/2 become a plus 1/2. All right, so now we're there. So now we get to do, what's the square root of all of that? Okay, so we got 1/4 e to the 4x plus 1/2 plus 1/4 e to the minus 4x. Okay, so hopefully you're all still with me here. A lot of algebra. But check this out. Check this out. So notice how this form, where we are right now, how that relates to the y prime squared piece. Look at those two. So hopefully you notice that they're pretty similar. In fact, the only difference is we've got a minus sign for the first one versus a plus sign. Well, if you look at that piece originally, the y prime squared, that came from squaring something. Well, that means this is coming from squaring something. And it's really the same thing, but with a plus sign. So if we kind of follow our way back, that came from doing this bit when we squared, right? So we were actually squaring this piece. Well, so the piece that we have here in our square root then, it's actually the same thing being squared except with a plus sign. Don't believe me? Square this out. Take that, square it out, do the FOIL, and you'll see that you end up with 1/4 e to the 4x plus 1/2 plus 1/4 e to the minus 4x. So then when I take my square root of that square, it ends up being this. So that's what's going to go in our first box. All right, well, guess what? We did only one step of calculus. All the rest of this was algebra. The calculus was just getting us to what I boxed in blue over here, right? This step was the one and only step of calculus. The rest of it was algebra. Ugh. Okay, well, now we have to go and finish doing our arc length. So if you haven't gotten this all down, take a real quick screenshot, because I'm going to erase a whole bunch here real quick. All right, but any questions on the algebra other than how the hell am I supposed to see this? Which is a legit question, by the way. I know a lot of times people are like, wow, I never would have seen that if you hadn't shown it to us. This trick happens a lot. It actually it happens a lot in math. So watch for it. Because if all you have is a different sign on the middle from a squared term, it just changes the sign in the original term. So just watch for it. Okay, well, let's actually get our arc length stuff now. Or sorry, no, we're not doing arc length. We're finding surface area. So let's get it done. All right, so for our integral, remember our surface area, we're integrating 2 pi RL. Okay, so for ours, we're gonna have 2 pi. The R, again, was the function. Because we're rotating, well, hold on. I'm gonna just double check and go back look. Yes, we're going around the x-axis. Okay, so we're doing this around the x-axis. So we're gonna take our original function, and then our arc length is what we just calculated over here. Okay, so that's what the integral is going to look like in order to find our surface area. We do need the bounds. I don't remember what they were. 0.1 to 1.2. And there you go. So this one, again, probably looks pretty ugly, but it's not terrible. I would start by distributing through, just to simplify everything. You're going to end up with, there's going to be a pi over 4 on the outside, because that's what's the pi you can see. The over 4, you can factor 2 out of the second set. That 2 and this other 2 cancels with one of the 4s. So you have pi over 4. Distributing through, you're going to get e to the 4x plus 2, because you're going to get e to the 2x times e to the minus 2x, which is 1. You're going to get another one from the I part. So this is the oi. And then the last, you're going to get e to the minus 4x. And then this is nice and quick because it's just exponential functions. So 1/4 e to the 4x plus 2x minus 1/4 e to the minus 4x. Plug in your bounds and you get whatever you get. We'll put a little smiley face just to make us feel a little bit better, maybe. All right, so these things get kind of gnarly, no doubt about it. Obviously, depending upon what your function is, the structure of the integral can get crazy. However, they're doable. They're definitely doable. This one just required a whole bunch of algebra that nobody really wanted to do. And yeah, there you go. So yet another story in the never-ending saga of algebra ruining calculus. All right, so good for this one. Questions on this guy? Like Hava put in the chat box, just needs to practice. Yeah, the more of these you do, the more you play with the setup and the simplification, the easier it's going to come. And I know nobody wants to do it. Nobody wants to do it. Just like nobody wants to go to the gym. It's not true. Some people like to go to the gym, but also some people like doing this because they're weird, right? But it's no different. I mean, it feels different, but it's not. You got to practice. You got to work out that muscle. And the only way you get good at this, the only way that you can, start seeing it the way I see it and be able to blow through it the way I do it, is practice. Again, don't compare yourself to me, because I've been doing this longer than most of you have been alive. Yeah, think about that for a second. All right. I mean, and I'm not even talking calculus. I'm talking about just teaching. I've been teaching at the college longer than most of you have been alive. I've been doing calculus for 30 some years. And algebra even longer. Yeah, I've been doing it forever. I actually kind of like it, right? I'm like that guy who goes to the gym every single day and doesn't mind leg days, right? You know the one that you just look at and you go, ugh. Right? I'm that guy in math, so realize that. But you can get there. You can get there. You just, like Hava said, you need to practice. Anyway, now I feel like I'm turning into dad, and I don't want to be dad. So anyway, all right. So yeah, homework. Surface areas and arc lengths. It's always the same setup, but it's definitely use of calculus. And the reason that integrals came about was because we were adding up little pieces, right? Remember, that's the whole key to integrals. Integrals are used when you add up things. So we've now seen areas. We added up little rectangular chunks, added up their areas to get total area. Volumes, we took slices or cylindrical shells, cut it into little pieces, right? And then added up all those little pieces. Arc lengths, take our curve and break it into line segments. Add them all up, make them small and add them all up. Surface area, same deal. So this is what integrals do. Integrals add stuff up. I know you want to say integrals find area. I mean, that's one of the things they do, but integrals are all about adding. So today, we're going to look at some physics examples where it's the same deal, where we just keep adding up lots of things. And when we add up lots of things, that ends up giving us an integral, and we can use the calculus. All right, so I'm going to hop over to the whiteboard, and yeah, we're going to do some physics. So I'll be right back with you. All right, so slightly different setup because I'm in a temporary location. Hopefully this works out all right. Got myself a whiteboard, and we'll see how this goes. All right, so what we're doing today are some physics examples. And physics is, well, as a lot of you know, physics is really just all about motion, getting things in motion. And you've already seen some use of calculus for physics. Remember those problems that were the old, here's an acceleration, find the velocity, find the position? That was physics. In fact, that's one of the more basic things that we do in physics, but there are a whole bunch more, and I definitely want to show you some of them today. All right, so the first one I want to talk about is finding weight from density, or mass from density. Oh, nice. So Hava just put in the chat, actually made it easier than the way I learned with physics without calculus. Yeah, when you take a non-calculus based physics class, stuff is just sort of given to you. You're just told, here's the formula, here's how it works. And I agree. I think once you are able to see the calculus behind it, it starts making sense. You're like, oh, now I understand. So yeah, I'm with you there, Hava. But I'm also a physicsy kind of guy. All right, so real quick, just to get things out. So mass is not weight. Mass is not weight. I know that we tend to equate the two, but they're different. Mass is just like, well, it's a property actually. It's called an inertial property. It's basically your resistance to motion. The more massive you are, the harder you are to move. All right, that's basically what it is. But mass is just a quality of all matter, and it's a resistance, ability to resist movement. When we talk about weight, weight is actually a force, and it's a pull on your body by the earth. All right, so when you step on a scale and it reads 180 pounds, that 180 pounds, that's your weight. That's actually the force of the earth pulling you towards it. Right? So your weight would be different on the moon. Your weight would be different on Jupiter, if there's actually a surface to stand on, right? But your weight would be different, but your mass would still be the same. Okay, so that's just physics. Bruce needs to make sure that we've got that out. Okay, so that's mass. And then density is just a mass per unit. So it's mass per length, mass per volume, or something like that. Some more housekeeping. When we talk about density, the letter that we use for density is the Greek letter rho. It's kind of like a curvy P. It's the Greek equivalent of R. This is what we're going to use for density. So if you ever see me write that, I'm talking about density, at least in this context. All right, well, basically, this is how we're going to find the mass of an object. If an object has constant density, it's really easy to get the mass. You just multiply the density by the volume or the length or the area or whatever our units are. So it's really easy if it's constant density. However, calculus lets us deal with variable density. So suppose that we just have a rod here. So we're just one dimensional. So think of it like a stick or something like that. So I've got a stick and I want to find its mass, but its density changes. All right. So maybe we've got it set up so that one end is heavier than the other. Maybe it's made out of a wood whose density is different depending upon where we are. Right. But we're going to go with just that. It's got variable density. So here's what we're going to do. We're going to cut it into lots of little pieces. I'm going to break this up into slivers. And I'm going to find the mass of each one. So basically, I'm just going to say, well, let's assume, and maybe this isn't a good assumption, but let's assume that we have constant density in each one of these little chunks. Because if we do, then all I have to do is multiply that density by its length, and that will give me the mass of this little chunk. Then I'll add up all those masses, and that gets me an approximate value for the total mass of this object. Okay, is this starting to sound familiar? Replace mass with area, or mass with volume, or mass with length, or mass with, this is exactly an integral. we're just going to break it into smaller and smaller and smaller pieces so that we've got more and more and more of them until they become infinitesimally small and we have an infinite number of them. And when we make them smaller, that assumption of constant density over that little length gets better and better and better. All right, so boom, next thing you know, integral. Ta-da! All right, so here's what we're actually doing if we're going to find the mass from a density function. All right, so let's just say that I know that my density is given by f of x. So we're only doing one-dimensional density. You can do two-dimensional, you can do three-dimensional. It requires calculus that you're not ready for, but you're going to get there. You'll be ready for it by the time you're done with the calculus sequence. All right, so trust me, if you continue on with our classes, by the time you've done your 4 quarters, you'll have seen how to do this for three-dimensional objects and two-dimensional objects. All right, but if this is our density, then it turns out that our mass is going to end up being the integral of our density function times dx. So if we're calling it f of x, we're just integrating f of x dx. All right, so all you got to do is integrate your density function and you'll get the mass. Obviously, you're going to put bounds on here, but those bounds are going to be wherever we happen to be on our x-axis. But there you go. There's a really simple, mass is not a complicated idea. So it's a real simple idea that uses calculus to find it. Now, of course, that would require you need to know the density function, which is not always easy. But if you've got the density function, that's all you got to do. All right. So I don't know that I'm actually going to do any examples because it's just a matter of integrating a specific function. It's not like we really have to do much to set it up. But this is how you can get mass from density. All right. So anyway, I can get the whiteboard closer. Let me try. Actually, the limiting value is where I've got my camera set up. But let me try something here. All right. So I'm going to pause just for 1 second here. Give me a sec. All right, so we're considerably closer. Unfortunately, there's a reflection coming from outside that I can't really adjust here. So I'll do my best to make sure that it's legible, but I'm glad that it's better. All right.
This makes me curious.
Cool. Find mass from density. If you've got a density function, you just integrate it and you go.
So
right.
this makes me kind of curious. Does this mean that that generally that density is like the derivative of mass if that's given as a function?
Yes.
Okay.
Yeah, if you have if you had a function that described mass, and that's where it gets a little bit weird, right? But you can imagine, okay, so my body, if you were able to specify where the mass is in my body, kind of distribute and all that, and get a function for it, then yes, if you differentiated that, that would give you the density function for my body. But we don't tend to do that. Mass is usually just a value, right? Like we go, what is the mass of Bruce? Not how is the mass distributed in Bruce? Although, I mean, there could be people that would be concerned with mass distribution, and if that's the case, and you got a function for it, then yep, its derivative would be density. Look at you using the fundamental theorem of calculus. Nice, 9:20 in the morning. Good job. All right, yeah, it kind of trippy when you start thinking about how all this plays together. All right, so there's mass from density. So here's another big use of calculus, and I would say that this is probably even more important than the mass from density thing, and this is work. Now, I don't know if you guys have gotten to this in your physics class or not. For those of you taking 107, have you started talking about work yet?
Like just started.
Okay. All right. Hey, cool. So this is very timely. All right. So work. Now, work is a little bit different than what we think of it in words, like in the English language. When we talk about something doing work or needing to do work, it's like an effort kind of idea. And in physics, that doesn't necessarily mean that work is done just because effort is applied. Because effort is more of an idea of force. But the idea behind work is this is energy that's used. I'm going to put here energy needed for a force Sorry, guys. Man, this is one of those days. I forgot to silent my phone, and all of a sudden a phone call started happening, and it buzzed right off my stand. All right. Hey, but I'm in Hawaii, so no complaints here. Anyway, I apologize. All right. So this is the amount of energy that's needed to actually move an object. So take, for example, oh yes, the roosters in the background. Yeah. And you can probably, there's all kinds of birds and jungle noises. You gotta love it. It's like, I don't know if you've ever had a chance to go to, I apologize for digressing. If you ever get the chance to go to Hawaii, you should, because it's the closest thing to being in a foreign country while still being in the United States, because it's completely different than anywhere else in the US. And it's pretty sweet. So yeah, Jurassic Park was filmed up on Kauai. And yes, Stephanie, same thing. In the morning when they wake me up, they've been waking me up at like 4 o'clock in the morning Hawaii time, which is like 6 o'clock Pacific. So I'm used to getting up that early. But every time they start going, I'm like, oh man, it's like I'm visiting Central America. So, anyway, so let's think about this guy right here. So just the eraser. So right now, if I let go of it, you know what's going to happen. Right? I let it go, it's going to fall because of gravity. So gravity just did work. Gravity did work to move this thing down. All right. So it's the energy needed for a force to move an object. Now, if I move this upward, there was also work done by gravity. But there's gravitational work as well, because there was motion. It's going to be the opposite of the work done this way. You just change the sign on it, right? But work is a measure of how much energy is needed for force to move an object. Now, you take that same gravitational force. Suppose I've got my eraser right here, and I move it this direction. Now, gravity didn't do any work. Gravity didn't make that motion happen, right? Gravity is just an up and down. That one, that was work done by me because I applied a force to move it. But in that case, gravity did no work, right? And if I just hold this right here and it's not moving at all, there's no work being done because work requires motion. And this is where I'm going to get to that. Work doesn't actually mean the same thing in the physics world as in the regular world. Because to us, am I doing work? Well, if this was a little bit heavier, it would sure feel like I was doing work, right? I put a book in my hand, I'm going to start feeling it in my muscles and all that, right? I'm not actually doing any work because I'm not moving it. I am applying a force, and that force is causing my body to start aching or whatever, but no work is being done because there's no motion. Okay, so the way that work is defined is you look at the force being applied over a distance. Okay, so work is, if you just wanted a formula, it's force times displacement. You take the amount of force and you multiply it by how much it's been moved. That's your force times displacement. So come back to this example. The force due to gravity is pretty much constant, 9.8 meters per second squared. Or that's its acceleration. I multiply by the mass to actually get the force. So it's however many newtons. But if I take that gravitational force and then I multiply it by the distance that it just traveled, so it was down here, now it's up here, that displacement times the weight is the work. All right, so it's just force times displacement. All right, now where this gets interesting is, what if this is variable? What if this force is variable? So it's not a constant force. And this we can even apply to gravity if we go far enough. Like if we send a, we're sending people to the moon. All right, so we're going to launch someone on a rocket up to the moon. The force due to gravity changes considerably on that person as they're leaving the Earth and going towards the moon, because it depends on your distance away. And so the distance to the Earth is increasing. And in that situation, we would have a very variable force. So if this is variable, we can't just multiply force times distance because that force is changing. So here's what we're going to do. We're going to break it up into little intervals. And we're going to look at this little chunk. Let's look at the force at this point and multiply it by that distance. And then we'll add this one, and this one, and this one, and this one, and this one. And then what we'll do is we'll make those little chunks smaller so that it's a better approximation. And then we'll let the number go to infinity. And then the next thing you know, we've got an integral, right? So for this one, if we want to figure out what the work done is, if it's variable, is again, it's an integral from A to B. Where it's f of x dx, where this force is given by a function f of x. So in that example with gravity, gravity follows what we call an inverse square law. it's the strength of gravity is inversely proportional to the square of the distance away. So it's a 1 over x squared. So your gravitational force would be something over x squared. That something depends on what objects are, right? Like the Earth versus the sun or whatever. But then you take that thing and you integrate, and you'll be able to find the total work done. Right? So there's your force times your displacement. Now I am going to show you an example of this one. And I'm going to look at a spring. All right, because this is kind of a classic example for work. So let's look at work done by a spring. Now, springs are kind of fun. I always loved playing with springs as a kid and doing stuff with them. But springs are kind of interesting because the force that they apply changes. So think about force. It's a push or a pull. Think about you've got a spring and you just start trying to stretch it out. At first, it's really easy. It's really easy to take a spring and either stretch it or compress it at the beginning. But the longer they get, the harder they are to stretch and compress. And so it turns out that the force applied by a spring, we look at it as an F here, it's actually equal to negative K times X. And let me explain what all this stuff is. So first of all, the X, this is how much it's been stretched or compressed from its normal state. Okay, so I'm just going to put here how much it's deformed. So if I've got a spring that's normally this long and I stretch it out, that change is Rx. Okay, so if we haven't pulled on it or pushed on it at all, and it's just a spring that's sitting in front of us, that's X equals 0. But as soon as you start tugging on it and making it longer or compressing it, then you change your X. But X is how much you've actually been deformed. So the more it gets deformed, the greater the force. Okay, so then the K. Well, this guy is what we call the spring constant. All right, now we got a truck in the background. This is going to be like the craziest video in my calculus sequence to watch. I think it was actually a garbage truck just came by. Anyway, so spring constant, K. This depends on the spring itself. The bigger the spring constant, the harder it is to deform the spring. So, for example, you guys know slinkies, right? I love slinkies. So slinkies are springs, but they're springs that have a very low K value. It's really easy to stretch a slinky, right? You've all done it. Take your slinky and pull it out and back forth, right? It's super easy. So it's got a really, really small K. Something with a big K would be like the springs that are in the suspension of cars. If you look at cars and where the wheels and everything are in there, there's some huge springs that are in there. And they have a very large K value because it takes a lot of force to make them compress and stretch, which is kind of the point. It helps balance out your ride by taking the force and deforming the spring instead of making the car go crashing around. Okay, so every spring has a K value. The minus sign is there because it's trying to go in the opposite direction. Think about when you stretch a spring. What does it want to do? It wants to go back. So it's actually pulling against you. Same thing if you try to compress a spring, what is it trying to do? Well, it's trying to rebound, it's trying to go back to where it was. So it's pushing against you. So that's why there's a negative on it. All right, so this is called Hooke's law. If you've ever come across that name, don't worry about it if you haven't. But this is Hooke's law. All right, well, if this is the force of a spring, we can actually calculate the work done on a spring. So let's do that here real quick. So we know that the work is the integral from a to b of your f of x dx. So if we come to this spring work, it's going to be an integral. We'll leave it as a and b for right now. But we're going to integrate negative kx dx. So let's go ahead and integrate this. So the negative k, that's constant. So we'll go ahead and pull that out. The x, super easy. Since that's x to the first, that becomes x squared over 2. And now we can do the fundamental theorem. Plugging in our a and our b. And I'm going to go ahead and distribute the minus k through. Well, I'm going to distribute the minus sign through. So that's going to swap those two guys. So this ends up being k times a squared over 2 minus b squared over 2. So we now have a formula for the work done by a spring. Ta-da! Super easy. All you need to know is the spring constant, and you would actually measure that by, like if you were in the lab and you wanted to figure that out, you would apply forces and figure out how far it stretches. And then you can use this formula to find your K. But then once you've got that K value, all you need to know in terms of how much work is done is your starting and your ending positions. What did the spring start as? What length were we off of equilibrium? And then where do we end up? You just plug those numbers in and you're good to go. Okay, so basically, if you know the force, you can calculate the work. It's that easy. All right, so another example of physics. But look at what we're doing. Same as before, we're figuring out how to break this into small pieces. We're thinking of this work idea as little displacements that we add together. Just like with the densities, it was little pieces of mass that we add together. Gives us an integral. Okay, so kind of a classic work done by a spring. But I want to show you another one that's kind of a classic work problem. And this is moving fluids, emptying a tank, pumping water into something. This is kind of a classic as well. And I really apologize for all the noise in the background. It's one of those things that you never expect. All right, so let's look at this. So we're going to look at work moving fluid. So suppose, just suppose, that we've got a tank. We'll make it cylindrical to make our life easy. and there's all kinds of water in it, right? So it's filled with water. But what we're going to do is we're going to take all the fluid out. We're going to remove all of this fluid out of the tank by way of a hose. So maybe we're going to like siphon it out. So we're moving it to another tank, let's say. All right, so we're siphoning this tank out. Now, to do this, we're going to have to do some work. We have to apply a force to move all this stuff over. Okay, so the question is, what's the total amount of work needed in order to move all of this fluid? All right, so simple enough question to ask, not necessarily simple to do, but it's a simple enough question to ask, right? So we know what's going to happen. We know what we're trying to do. All right, so here's how we want to think about this. We want to break this down into smaller chunks. All right, and here's how we're going to do it. We're going to think about this fluid of, or this container of fluid as a whole bunch of pieces. And we're going to find the work done on each of those pieces to get it out. Make sense? All right, so here's how we want to think about this. We're going to be looking at work. The work done is going to be against gravity, right? We're fighting gravity to get this water out. We got to lift the water, basically. So in this case, because it's a small tank, we're going to go with gravity is constant, that the force due to gravity is constant. It's the weight. All right, the force due to gravity is the weight. So if we know the weight of the water or the fluid, then super easy, right? But what's going to be changing, and remember to do calculus, we have to have something that's changing a bit. What we need to be changing in this case is the distance that it has to move. Right? Like think about this. To get this out of the tank, we have to get all of the water to the top of the tank, basically. Because once it gets to the top of the tank, it's removed, right? If we wanted to be smart about this, we would have this hose coming out so that it doesn't go any higher than the very top of the tank, right? So that we don't have any extra height for it to go. But that's going to change, right? You think about the bit on the bottom, it's got much greater distance to travel to get out of the tank than the bits at the top. So it's actually the distance that this has to travel that's variable, not the force. All right, so here's how I'm going to divide my fluid up then. I'm going to divide it into chunks such that all of the water in the same chunk has to move the same distance to get out of the tank. All right, well, in this case then, that means I want to look at a little horizontal slice right here. Because if we think about all the water that's kind of in this purple line, all of that needs to move the same distance. It's got to move this distance, let's just call it X. But every drop of water that's in that slice right there is going to be moving the same distance for the distance part of work. If I looked at another slice, let me go down here to another place, I'll make it black. Yeah, let's actually just use this one. So let's just think about water that's right there. All of that needs to go the same distance. It's a shorter distance. So another X over here, but it's got to move a different distance X. So here's how we're going to break this down. We're going to break it into a whole bunch of chunks where those chunks are things have to move the same distance. All right, so let's start thinking about how work plays out, right? We have to get, it's the integral of force times displacement. All right, so we already saw that the displacement is variable, and in fact, it's going to be x, the way I've kind of got this thing set up. So now we have to calculate force. So force, that's going to be the force due to gravity. So Aries, isn't it all getting pumped from the bottom? Yes. Yes, it is. However, this is where it doesn't really matter that happens, because think about this black line. Okay, so think about the water that's at the black line. Yes, it's going to drop to the bottom and then work its way back out. But the work done from this black distance, the distance of the black line down, is opposite in sign to the work required to get it from the bottom back up to this black line. Remember when I talked about this versus that? So here's what happens. Whatever this is as it drops, when I add it to bringing it back up to this level, it gives me actually 0 work. Okay, so if you were to follow one of these chunks of water in its path, and we come down and then we come back up, by the time we return to this level, we're still at 0. And so if we're going to figure out the net, like what, at the end of the day, how much work was done, we only have to worry about then the remaining, get it out of the top of the tank. So I appreciate where you were coming from, and that definitely does matter. So for example, if instead of siphoning it out, we had a drain at the bottom, then it's a completely different question. Because now, as things drop, they leave. That's a different amount of work than down and back up through the top. So it is important to pay attention to where it's leaving. So I'm glad you kind of saw that. But in this case, yeah, it turns out it doesn't really matter, because the return trip brings you back to 0. It's because gravity is what we call a conservative force. Physicist Bruce is coming out a lot today, and physicist Bruce covers his ass a lot with lots of statements. But gravity is what we call a conservative force, and because it's conservative, the work done on a round trip is 0. That's not always the case. There are forces that are not conservative, like friction. That one, you do a return trip, the total friction work is not 0. In fact, it's greater because of the fact you go down and up. All right, but in this case, yeah, we only have to worry about how far we have to get to the top of the tank for it to. All right, so let's see if we can figure out the force. So the force is gravitational force, which means it's the weight. So we need to know the weight of that slice of water. All right, well, let's think about how you would get that weight. You would need a density, and probably a density per volume, right? And so if we're going to get our weight, it's going to be density times volume. Well, the volume of that slice is going to be its cross-sectional area times its thickness. If that sounds familiar, it totally should, because remember, that's how we did volume by slices, cross-sectional area times thickness. All right, So that's what's going to go in for our force. It's going to be that weight, which is our density times the cross-sectional area times our thickness. All right, well, think about putting all that in. When we have an integral, we have to have a differential. We have to have a little dx or a dy. And in this case, where it's coming from is the thickness, just like when we did volumes before. So you may remember with Hooke's law, it was the displacement that gave us the dx, gave us the differential. For this one, it's now the force that's giving us the differential. So with work problems, you will see both of those. Sometimes they're set up so that displacement gives you your differential. Other times it's your force that gives you your differential, but it's always going to show up somewhere. Okay, so let's see if we can actually answer this. Let's put in some numbers for this tank, and let's see if we can figure out how much work actually has to be done. So we're going to empty this tank. Let's say that we know that it's 3 meters tall. All right, so we're going to say that this right here is 3 meters. I'll even tell you that the radius is 1 meter. Okay, so this is a good sized tank. Right, all the way across is a little bit more than my wingspan. So imagine I've got my arms out all the way. I know you can't see it in the video, but that would be how far around this tank is, a little bit more than that. And it's 3 meters tall. So that's around 10 feet or so. So it's a large tank. Maybe it's a tank that's used at a brewery or, you know, a place that makes like soft drinks or something like that. So it's a big container for brewing high quality root beers. All right, so we got, this is our size, and we're going to be working with water, just plain old water here. And what I can tell you about water is that its density is 1,000 kilograms per cubic meter. So for water, 1,000 kilograms per cubic meter. So it's fresh water. Obviously, salt water, like you go into the oceans, it gets higher depending upon where you are, right? It's usually around 1030, something like that. If this was a container of root beer, the root beer is going to have a different density. It's going to be a little bit higher. Well, depending on whether it's regular or diet. Did you know that diet sodas are less dense than water? Well, fun fact, next time you have a bunch of different kinds of sodas and they're in like a cooler, you know, big cooler that the ice is melted and turned into water, you'll notice that some of them float and some of them sink. Just notice this the next time you're at a situation where you see that. And you'll see that the ones that sink and the ones that float, some of those, it's the diets versus the regulars. I'm not going to tell you which. I'll let you experiment on there. Anyway, density changes is the point. I'm going with fresh water. Man, I'm in a mood today. I guess I haven't taught physics in a long time. Anyway, all right, so there's our density. So believe it or not, we now have enough information for us to calculate how much work is required to empty the tank from removing stuff from the top. All right, so here we go. Let's see if we can do this. So we need to do force times displacement. So we know the force is the density times the cross-sectional area times the thickness. So let's get that first. All right, so we start setting up our integral. And have our work is equal to, we'll worry about the bounds in a little bit. But let's start with, we need our density. We're going to have our 1,000 kilograms per cubic meter times our cross-sectional area. Well, this tank, the cross sections are all circles, and they're all circles that are exactly the same. So we just use our good old pi r squared. So there's the area of the cross section, pi times 1 meter squared, pi r squared. You can imagine that if we had a different shaped tank, that cross-sectional area could change. Like what if this tank was conical? Think of it as a cone. Again, you've got circles, but those cross sections are going to change as you move up or down. What if it was a spherical tank? Again, cross sections are going to be circles, but they're going to be changing in size. What if it was a tank that was like a cylinder on its side, like a propane tank or something like that? Well, they would have cross sections that are rectangles, but their sizes are going to change as you move up and down and so on. So, but this one's nice and easy. We've got constant cross-sectional area. So pi times 1 squared. All right, now we need the thickness. Well, the thickness of one of these little slices is going to be dx, because we're going to make them infinitesimally thin. Super, super, super thin. Because then we're going to add them all up. Okay? So there's our cross-sectional area times thickness times density. Okay, so there's our force. Ooh, it's the soundtrack to calculus. I don't know if you can hear the country music that just started across the street. All right, so now we need to think about displacement. So how far is any one of these slices going to move? Well, it's going to have to go the distance to the top of the tank, which I'm calling just x. All right, so here's our force times displacement. And our integral is set except for the bounds. All right, so before I attach bounds, how are we doing? Thumbs up? Ish? Questions? Okay, I'm seeing thumbs up. I like it. All right, so the last thing we need then are the bounds. So we need to look at the x. What are the bounds on x in this case? Well, those are the distances that these slices have to move. All right, well, the very bottom slice, the water that's at the very bottom of the tank, has the greatest distance it has to move, which is 3. So that's going to be the upper bound on this one. The lower bound, the least amount of distance that this fluid is going to have to travel. Let's assume the tank is completely full. If it's completely full, then the very top layer doesn't have to move at all. It's actually right there. So our bounds there would be 0 to 3. So this integral right here is going to get us the amount of work that we need to do to empty this tank. All right, well, notice that almost all of this is constant. I've got 1,000 pi, so I can pull that out. I'm integrating x dx, so that's going to give me x squared over 2, going from 0 to 3. So I can plug in my 3, I can plug in my 0, and let's see what that gives me here. Divided by 2 is 5 times 9. Should be 4,500 pi. We could use our calculator to get this value, but I'm just going to call it 4,500 pi. And the unit on this, just so everybody knows, the units are joules. So we use a capital J for that. It's named after French physicist, but joules are units of energy. All right, so that's how much work would be required to empty this tank. It's also how much work would be required to fill the tank. If we were starting with the hose down here and pumping stuff up. So people, this matters to lots of people. For those of you who are thinking about going into civil engineering, this is a big deal. Because anytime you have fluids moving, think water lines, sewer lines, things like that, you definitely have to pay attention to how much work is done to move things around. All right, well, similar to this is fluid pressure, how much force is actually being applied, say, on the sides of the tank. And we'll do that example next, but that'll be next time. That'll be on Wednesday. All right, so I'm going to call it for today. We're not quite done with the next section. I think we're in, don't quote me on this, I think we're in 2.5, I think. I don't really remember the section numbers, but I think this is 2.5, and we're almost done with it. I just need to show you fluid pressure. But next time, we're going to look at fluid pressure, which is another example. And then we'll do some more physics examples. So this is going to be a couple days of physics examples. So plan on Wednesday being more learning about physics. All right. Okay, so just a couple reminders. Don't forget there is homework due tonight. A couple of sections that are due tonight at midnight. So make sure you finish those off. All right. But other than that, I have nothing else for you guys. So I'm going to go ahead and stop our recording.